Today, we want to continue doing old problems way back from Calc 1. We know about these things called partial derivatives, so here is what we want to lead with. We're going to upgrade our find the equation of a line tangent to a curve at a given point to find the equation of a plane tangent to a surface at a given point. The given information is similar. I give you a function, but of two variables this time. But now, instead of just giving you an x value that you have to go plug in to find the y value, I have to give you an x and a y value that you'll plug into the function to find the z. Here's the core thing. We want the equation of a plane. And I'm going to mark this up. Now, you didn't see Calc 1 yesterday, but I marked it up the exact same way. We want to find the equation of a plane. And we know that for the equation of a plane, we need a point, a slope, and another slope. They're not really called slopes. There's the dz dx and there's the dz dy. But we need two of those. The part where it says tangent to the surface, and we have with our function of two variables, the tangent part says that the slope comes from derivative. So this tangent business says we'll use derivatives to find the slopes. That's what tangent does for us. We've had to increase the number of things that we were given. I gave you a point -3, 4. So I gave you an x naught and a y naught instead of just x. Instead of just saying when x equals 3, I got to give you an x and a y. So imagine the plane. Here's the point -3. It's out in the hallway because I didn't want to draw it, so you can't see it. So -3, 4, and then above that point, there's this surface. What does this surface look like? That's a new thing. The one that I used yesterday in Calc 1 was a parabola because it was just like this, and it wasn't 29 because I didn't need to go that high. What does this surface look like? That's one of the things that we need to be building. What's this surface look like? We can see that it has circular cross sections because it's 29 minus the sum of x squared and y squared. So the surface is a circular paraboloid. We just start off with 29 and it drops down. Z equals x squared. That's parabola stuff. So it's a circular paraboloid. So it's just like a parabola that's been rotated around in a circle. Circular paraboloid. That's what we want to see when we see that 29 minus x squared minus y. If you're having trouble seeing the circles, there they are. Now we just need to go through and find our list of stuff. We need a point. And to get a point, we'll just plug x naught and y naught in to find z naught. Suppose I don't need to call it z naught, but I'm gonna. I picked 4 because one of my options was to use a sphere. And then I was going to have to take the square root of this, and I didn't want radicals running around. And then I said, you know, just go with the paraboloid. And that's when I came up with use 29. And then, anyway, like I said, this is just me not having time to process this morning because of the fire alarm. Mostly because I don't like using -3, 4, and 4, because so we get all the x's and y's confused. But that's okay. We've got a point. Our point is -3, 4, 4. Now we need multiple slopes. We need a change of z in the x direction and a change in z in the y direction. So now I need 2 slopes. Let's include all the notation. So our partial of z with respect to x, our slope in the x direction, will be fx at x naught, y naught. Fx is pretty easy to find. Fx as a function is just going to be -2x. So fx at -3, 4 will be -2 times -3, or 6. So there's our dz dx. We want the equation of a plane. A plane has a change in z with respect to y as well. And that's going to be fy. I spelled y wrong. So I'll take the derivative with respect to y and then evaluate it at the point -3, 4. Fy, once again, nice and simple, -2y. So fy at -3, 4 is -2 times 4, or 8. Now I have what I need to build the equation of my plane. -8. Thank you. Now I have what I need to build the equation of the plane. So because I have this point and these 2 slopes, that I'm going to want to use my point slope form, and I'm going to write it as a function. I'm going to use the z equals z naught plus dz dx times x minus x naught plus dz dy times y minus y naught. I should indicate that the dz dx and the dz dy are evaluated at the point x naught and y naught. But I didn't. I usually don't because it's messy. So our equation will be z equals z naught 4 plus dz dx times x minus x naught negative 3 plus minus plus a negative 8 times y minus y naught, which is negative positive 4. We're following the same progression that we did in Calc 1. We learned how to take derivatives. Then we use those derivatives to find the equation of the tangent line. Any questions? How's everybody okay? It's really bugging me that I used the 4 because there's the y and the z are the same. I really don't like doing that. It's one of the things that bugs me about the textbook. There are so many integrals, like when you're calculating integrals where the x is from 0 to 1, and y is also from 0 to 1. I go, come on, how can you tell if they're setting up the integral properly if x and y have the same limits? It's really annoying. You know what I mean? Not really, because we haven't got to double integrals yet, but when we do, I will be angry about it. Not like really angry, I'll just change. X goes from 0 to 2 and y will go from 0 to 3, then I can tell which ones you're looking at. You know what I mean? No, you don't. We haven't got to double integrals yet. I'm gonna put, you know what I mean, on one of the on a quiz, and it's gonna be yes or no, and you're like, oh man. Then you'll send me an email. It's like, well, I don't know what to do on this question. Then I will respond with, well, I guess you know what the answer is then. So we're finding the equation of the plane tangent to a surface at a given point. Planes are what happens with linear functions. Planes are the result of a linear function of 2 variables. So the tangent plane, just like the tangent line, is our best linear approximation of the function near a point. This is the same thing that we had with tangent lines. Tangent lines were the best linear approximation of a function near a point. Tangent plane is still the best linear approximation of a function near a point. So we could, for example, let's say negative 3.1, 4.2, now, at this point, it would be ridiculous to do this. We actually have the function in our hands. Just plug the 3.1, negative 3.1 and the 4 into the function to find the value. but that doesn't illustrate what we want. We're pretending that we don't know what the function is. It's off the top of the page anyway, so you can't see it. It's not there. Gone. So all we have is this linear approximation. It might be that this is all we've got because we looked at our data and we saw how z was changing in the x direction, and we saw how z was changing in the y direction. We don't know what the function looks like. So we're just going to have to approximate what's going on near that point. And we just plug it into our linear function. One of the reasons I don't want to write this all out is so that we can see that negative 3.1 plus 3 show up as negative 0.1. That's our delta x. And this negative 8 gets multiplied by 4.2 minus 4, or plus 0.2. That's our delta y. So this negative 0.1, that's a delta x. This positive 0.2 is a delta y. The 6 is delta z over delta x. So it's like we cancel out the delta x's and it tells us how much z is changing. So 6 is the delta z over delta x. And the negative 8 is the delta z over the delta y. So when I multiply these, I get 4 minus 0.6. If I take delta z over delta x and multiply by a delta x, the delta x's cancel. That's our delta z, how much z is changing. That's the contribution from the x changing. And then minus 8 times 0.2 is minus 1.6. That's our delta z, because we took delta z divided by delta y and multiplied by a delta y. So the 4 minus 0.6 is a 3.4, minus 1.6 is a 2.4, minus 4, 1.8. There's a delta z from the change in x and a delta z from the change in y. So we end up at approximately 1.8, which seems like a big change, but look how steep our function is in the y direction. And look how steep our function is in the x direction and how we're going backwards. Any questions? Also, think about what our surface looks like. It looks like a paraboloid. And the top of the paraboloid, where it's most round and the flattest part, that's way up at z values of 29 near 0, 0. We're way the heck off here at negative 3, 4 at a height of 4. So that's pretty far away. We're pretty far away from the vertex. Things are going to get pretty steep in our parabola when we're that far away from the vertex. Think about the function y equals x squared. It's all flat when x is equal to 0. But when we get 25, when we're at values of 25, it's getting pretty steep. At 0, we have a slope of 0. But when x is equal to 5, we have a slope of 10 or negative 10. That's pretty steep compared to the flat part. So we're on this very steep part of the parabola. So it makes sense that we should see massive changes when we're this far away. Any questions? Comments? Snide remarks? How's everybody, okay? Equation of a tangent plane. It's the same game that we played before, but it's a plane. So instead of a point and a slope with a line, we need a point and two slopes. This allows me to bring up an important point on the quiz. I did not put sufficient number of answers, of correct answers on the quiz. And in a class this size, y'all are going to find things that I didn't account for. So on the quiz, you might have the correct coefficients, because I asked for standard form and I asked for integer coefficients. So if you've got fractions, multiply out your fractions to get integer coefficients. Also, if all of your coefficients have a common factor, divide that out. I kind of did this automatically. I'm like, oh, this will be fine. And it wasn't fine. So if you've got like, I can't remember what the spread was, but if you've got like 10, 12, 20, and 4, everything has a factor of 2. Divide out the 2 and see if that works. I realize it means you have to submit the whole quiz again, even the 2 that you got right. But that might be the only problem. If there's no common factor, make sure just multiply everything by -1 to see if I forgot to put that one on. Because if it was like -5, 4, 3, and 6 or whatever it was, I might have forgot to include 5, -4, -3, -6. This is because I can't think of everything. And I wanted things to be gradable like instantly. I wanted you to be able to have the results right away. You know what I mean? So I might have messed that up. So think, you know what? I think I did all this stuff right. Let me just see if I got a multiple of the answer. So try a different multiple. You have unlimited attempts and the highest one counts. So I realize it's kind of a pain in the butt to go back and resubmit those things. But that's just the way that I built the quiz. Any questions? So I apologize for the inconvenience there, but it's kind of convenient for all of us so that you can have the quiz graded right away, because you don't want to wait for me to be grading a quiz, because I will just forget. I will have moved. I forget to grade quiz 2, and I will just have moved on to quiz 4. I'm like, oh, what should we have here? Are you going to grade this quiz? I'm like, well, I'm sure my assistant will do it. You don't have an assistant. Bye. So it's like a whole thing. I can't keep all of that in my memory. But to actually have an assistant, I would have to get a PhD and be at a university. And then I would just be distracted by publishing. So I don't know. I don't know what the answer is. I'm certainly not going to go back and get a PhD. I don't think I could compete anymore. So, you know what I mean? All right. That's the day. I really just want you to see how similar this is to the stuff that we did in Calc 1. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.